And here we go. We have liftoff. Propulsion continues to be normal.
R68 chamber pressure looks good.
Following up. Roger, roll, planet.
Water towers fly! Yes!
Tango down to nominal.
Flight downside FD off. Bring in FD off. Off. It's orange!
145. Oh my god! Oh my god!
Decollage.
What is it?
Put that in the big bag,
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
If the methane would be igniting in the flare, correct?
Yikes. You dead? We don't need any more of these.
All right, folks, you know the drill. Let me know if you can hear me and see me right now. John Galloway for NSF. It's time. Little things jumping up and down like it's supposed to. The audio bar is jumping up and down like it's supposed to. It is time for this month's Intrepid Museum Astro Live in partnership with NSF. If you're watching on the NSF channels, once a month, usually, we come through with Intrepid Museum and we have a cool guest with you. We have astronauts, we have engineers, we have all sorts of folks, and we sit down with a one-on-one conversation, or sometimes a two-on-one or three-on-one, whatever. People sit down and talk to us, right? Once a month as part of these Astro Live shows. So this month, we've got a very cool guest. If you read the description of the stream and stuff like that, you would know that we're going to be chatting with the chief engineer of Ingenuity, the helicopter that did 72 flights on Mars. The helicopter on Mars is the first part of it. Like, wait, what? We can do that? Of course we can. JPL did it 72 times. Is going to be here to talk to us about the mission and walk us through a bunch of the accomplishments and challenges and stuff like that they came up with. So this is a live show today. If you have questions for us, you can tag us in chat at NASA Spaceflight on the NASA Spaceflight channels or Intrepid Museum. Just put a question in chat on the other ones. The chat seems to be a little bit slower in some of the other channels, so it's easier for me to pick them out. But if y'all have a cool question that's relevant to something that we're talking about, I will see if I can't grab it out of chat, and we'll ask our expert, who is here from NASA. Also with me today, Elysia Segal. You know her. Ask about her earrings when we get her on camera here. She will be joining us on the stream today. But real quick, couple housekeeping things beyond the asking of questions. We're doing a fundraiser for the museum today. If you see down at the bottom of the stream, you should see that there is a fundraiser involved. And if you support that fundraiser, that goes directly to the museum. 501c3 is the right way to say it, I think, nonprofit educational outreach programs. So that's a thing. Now, I'm not going to go through and read them all because we're going to give all of our time to the guest, right? But if you do support the museum, it helps it so we can continue to do cool things like this. Mouth is running at 104% of rated capacity again. Sorry, I can't pronounce things. Look at that. Wow, somebody already did $50 for the museum. Thank you for the support. Hey, also, these shows are made possible through a grant from the New York Space Grant Consortium awarded to Intrepid Museum. Shows don't just do themselves. They do take a little bit of time and effort and resources to get going. So massive thanks to the New York Space Grant Consortium for helping us continue to make these things possible. That's enough about me. Let's get our guests in here. Let's see if all this audio and video is working correctly. And please welcome to the show, Travis Brown, Ph.D. I guess this way is the way to point over here. How's it going, Travis?
I'm good. Happy to be here.
Excellent. Thank you so much for taking time out of your weekend to talk to us about the accomplishments of robots on Mars.
Anytime.
All right. And you'll know Elysia as well. Elysia, how you doing?
Hi, doing great. And yes, thank you so much, Travis, for being here. You know, the topic, we specifically wanted to revisit this. I don't know if you guys, if you're long-term followers of, Astro Live or the museum or NSF Live, really. But we actually had Teddy Zanettos, who is at JPL, who's a colleague of Travis's, who was talking about Ingenuity 1 year after everything landed. So that was 2 years ago now. And at that point, they had just completed, I think, the 19th flight, which is wild that now we're in like the 70s, right? Yeah. But they were just it had just finished the 19th and they were just about to start like that Northwest Passage and everything. So we were like, you know what? Ingenuity has had an amazing run. It is time to honor Ingenuity, give it its last, 21 gun salute send off, Thank you for your service. And recap what has been going on in the past few years, because it's been a while, and Perseverance and Ingenuity both have done some amazing things up there on Mars. So we're so excited to have you on to recap all of this and to kind of, fill us in on what's been going on.
There you go. Well, let's jump right into it here. Y'all know we don't have like a script or anything like now talk for 3 minutes about this. What we do have is a map of Mars. That's available online, actually. Let's put this link into chat, so if y'all want to follow along or click on things on your own. This is actually from the mars.nasa.gov website, and we're going to be using this to sort of talk through where the rover and the helicopter went and what they did. But Elysia, Travis, I'll turn it over to y'all. Where do y'all want to start? I got a bunch of stuff to show people.
Well, sure, yeah. So, Ingenuity, first of all, it's this incredible thing, right? So it was a technology demonstrator, first of all. Again, only supposed to have 5 flights. And I believe it was only supposed to be like 30 days, right? And amazingly now, it has had 72. And of course, in the news recently, it is no longer with us, sadly. But first of all, as a technology demonstrator, the idea of this helicopter on Mars, it's something that's kind of wild, because the atmosphere is the air is like 1%, I think, the density, right, as it is here. So to even come up with something, how those rotor blades work, how on earth this is even a thing, can you just kind of give us a brief summary of who came up with this idea? Why do we have something like a helicopter on Mars? Why would we want to have something like that? And how did this even happen in the first place to get to where we are today?
Yeah, so I think the initial concept's been kicked around for a while. The atmosphere being 1/100th Earth atmosphere, it makes it difficult, and so it's always been a little bit of a the physics technically closed, but could you engineer it to make it work? It's always been a little bit of a trick. And I think it was really looked at seriously back in the 90s and 2000s. Bob Ballaram, actually, who was the original chief engineer of Ingenuity, and I think you could say the father of the helicopter, he's the one that kind of got it started originally. And then in the modern development cycle back in the 2010s, that's when Bob met with the JPL lab director Charles Lacci. They started talking, and they said, hey, let's try to make this happen. And the rest is history, right? They were able to put a team together. They did all the testing necessary. They got the vehicle working. It takes a couple different tricks. One, it has to be very, very small. The blades have to be extremely large, and they have to rotate very fast. Mm-hmm. And that's kind of the main 3 physics tricks that you have to play to get it to work. There's a lot more to it than that. It turns out, controlling it and all of the packaging and the energy and everything else is incredibly tricky. But yeah, we put together a helicopter. We did, I think, the initial proof of concept flight, where we actually were able to fly in a Mars atmosphere here on Earth in our 25-foot chamber, was in 2016. Yeah, so there we go. We got a video of that, or a picture. So yeah, as of 2016, we knew the physics worked, and we knew that the control worked, and we knew that we could do it. Now, actually getting it on Mars turned out to be, in some ways, a lot harder, because we were, as you said, a tech demo, and there's not a lot of money for tech demos, and getting to Mars is very expensive. And so the way we solved that is by piggybacking on the Perseverance rover. That adds mass and risk and takes up space on the rover. So the rover team wasn't particularly thrilled with the idea of us kind of being this parasite on the back of the belly of the rover. But there it is. We managed to get it through. There were a couple different points where it looked like maybe the project was going to die, just again because of concerns that it might jeopardize the broader, more important mission that Perseverance has. But through various people coming to bat for us and the politics of NASA and JPL, eventually we were able to get it approved. And every time that it looked like there was some showstopper from an engineering standpoint, our team would come through and show that no, this thing is good to go. So it was quite a wild ride. There was a roller coaster of emotions throughout much of the project.
And there still is, even today. I remember one of the things that Teddy told us too a few years ago was that the parts for it were all like off the shelf items too. You guys were able to just be very scrappy in terms of how you put it together as well. And yet here it is. It's just, proof positive that you don't need a ton of funding. Even you just
Yeah, I mean that's right. Actually, it's kind of interesting. The electronics we normally fly in space are very heavy and very expensive, and that's because they have to be tolerant to radiation and wide thermal extremes, right? So space is hot and cold, and there's radiation pouring in all the time, and so we tend to fly these really bulky, very expensive electronics that can handle it. And so in this case, we just didn't have the mass or the space to afford those electronics, not to mention the money, right? So we got kind of pushed in that direction. And there's one way you can do it, which is that you design things from the ground up to be tolerant to that stuff. And then the other way is that you just find parts that happen to be tolerant. You put them in the chamber, you test them, you thermal cycle them. And, if you're choosy and you're selective, you can get parts that work, as we did here.
Can I ask I have a question from chat real quick.
Sure.
This image here, it looks like the stage, like behind the stage at a high school, like gym or something like that, but it's not. It's a special chamber y'all have where you can control the environment in the chamber. And this is where you actually it was proven that the helicopter could fly in low atmosphere. Like, did y'all pump this chamber down so the atmosphere was thin like Mars?
Yeah, so this is the 25-foot chamber at JPL. This is actually a National Historic Landmark. It's one of the largest thermal vac chambers in the world. And as the name implies, it's 25 feet in diameter. It's actually very, very tall, which is good for us because we needed that headroom for the gravity offload system.
Yeah.
But yeah, you can pump this thing down to vacuum. You can put Mars conditions. You can go anywhere from hot to cryogenic. So you can replicate a wide variety of kind of planetary atmospheric environments here. And so, yeah, this thing was pumped down to Mars atmosphere, filled with CO2, which is, Mars atmospheric composition, taken down to Mars temperatures. And we were able to prove for the first time that we could actually fly. Until that point, it was models and physics simulations.
Yeah.
And when we actually got it flying here for the first time, that was the first time we knew for sure the physics worked.
It had like a gravity offload system, you said? Is it that like picks up part of the mass of the helicopter, or I guess the weight of the helicopter technically? So you were simulating Mars. Yeah, go ahead.
So it's always a problem here, right? That we don't have the ability to generate gravitational fields, right?
Yet.
So testing things that are meant to operate on the moon or Mars where gravity's different, it's always challenging. So the original test flights in 2016 occurred on a vehicle that was just the blades and the motors. So it weighed less. And so when you accounted for the fact that you were in 3 times the Mars gravity, it was correct, right? When we started building the final system and adding the batteries and the avionics and everything else, this vehicle now was correct mass, but 3 times heavier than it should have been, if it were flying on Mars, right? Because of our higher gravity. And so to test that version, we did need to construct a gravity offload system, which was essentially a very long, thin piece of wire attached to the top of the helicopter that just applied a little bit of force to offset the gravity difference.
Gotcha.
Yeah. And then in terms of, so originally it was only supposed to be 30 days. So you knew when Perseverance was going to be landing. So you knew roughly, I guess, what the temperature would be like. But did you guys could you have ever imagined that it lasted, it would have lasted as long as it did? But as a result, then also, seasonal changes on Mars. Did you kind of also test out how that might affect what the air would be like as well? Like if it's warmer, would it be like thinner density or anything like that?
Yeah, that's right. That's right. So we landed in we landed in the spring. So this was intentional, right? The missions tend to try to land in the spring because that's when you get the nice temperatures and the nice sun and everything like that. It's the most benign conditions you can imagine, right? And we designed the helicopter to operate at that level. And one of the big things that people don't know is that the thermal design for Ingenuity was quite difficult. It's basically sitting here, it's this tiny little box on Mars, right? Very, very small, and it has to keep itself warm because, again, these are off-the-shelf components. They're not rated for these wild temperature extremes. It'll get down to minus 60, minus 80 Celsius on the surface, right? That's like dry ice temperature, or colder. And so it basically the power budget was primarily allocated not for flights, but just to keep the helicopter warm. And so we designed the whole system to work in spring, and it flew. And honestly, we say 30 sols or 30 days and 5 flights. That's the kind of nominal mission that we were shooting for. But I think most of the people on the team would have been happy with, mission success would have been if we had flown once, right? That was kind of the level of expectation, because we were doing something that had never been done before.
Right.
After we did, several flights, and it became clear that the engineering was largely holding together, then yeah, I think we sort of expected it to operate for the rest of the spring and the summer. When fall hits on Mars, in the northern hemisphere anyway, you get this huge uptick in dust storms, and the atmosphere gets really cloudy. And at the same time, the sun's starting to drop down in the southern hemisphere, right? So you get this kind of 1-2 punch of dusty atmosphere plus less sun to begin with. And when that happened, actually, we sort of ran out of power. We just couldn't keep ourselves warm anymore. And the low-level electronics took over, and they cut power so that you don't fry stuff. And at that point, it was not clear that we would survive, right? These are all off-the-shelf components. I think the biggest concern was, hey, we would go down to -80 and we just never come back. And it took us a while. It was a couple weeks, but we did eventually find the helicopter kind of doing its standard automatic boot up sequence as if it had just landed on the surface of Mars, as if it had just been power cycled. And that was a great piece of news, right? Because that meant, hey, we can survive in the cold. We may not have enough sun to fly a lot, but we can survive. We're not dying. Now, we did take some casualties. The inclinometer died. That was one of the off-the-shelf components that didn't like the deep extreme thermal cycling, but largely the vehicle was intact. And so then we see in the flight log that opened up that was more than half the mission, more than half the flights. Let me see if I can remember. So this would have been like flight 25, I think. Here. Yeah, so this was like more than half of Ingenuity's flights occurred after this initial brownout. So you can imagine that if we had died then, there would be much less mission. Yeah,
I think I can bring some of those up, because this is sort of like the landing zone, right? Where it did the first flights, and these are, if you hover over these, y'all, if you're following along at home and you hover over these, you can bring this out on the side by clicking this little layer thing here, and you can turn on and off different things. So to get the helicopter waypoints, you need to turn on helicopter waypoints. I just figured that out. And so you can hover, and there's like flight 6, flight 7, flight 20, and that's when you get over here, flight 21, flight 22, flight 23. So Travis, you were just saying that you had the brownout, and then that was flight, what number was that in between?
Yeah, here, let me walk you through it really quick.
Yeah, sure.
So you can see that we landed and we dropped off where you were hovering and saying flight 1, 2, yep. Right? So we kind of tooled around there. And for the first 30 days, the rover had a mandate to support us to do our tech demo, right? So we started small. We did short hops at first. The first flight was like 10 feet off the ground, 3 meters. And then we started sort of moving side to side and verifying that all of our models are holding up. After that 30 days, then the rover's like, okay, we're done with your tech demo. We're now going to go on with our science mission. And so you can see the rover starts driving around, and we were still around, and we successfully lobbied for additional funding to start proving Ingenuity now, not as a technology demonstration, but as an operational asset demonstration. So that is sort of as a scout, which is what everyone immediately thinks of when they think of Ingenuity on the surface. And so that happened after the first 5 flights. So you see that flight record, we start going south. We basically try to catch up and track the rover's progress. The rover's doing a lot of different science there. They're driving around. And then it became clear that they were going to go up and around. If you zoom back out, they had this big circuitous white path, right? So that was kind of the plan. They did some work down in the south, and then they were going to go around. Yeah, that's right. So,
how's that?
So it's kind of an interesting thing with Ingenuity, because we can fly more in 2 minutes than they can drive in a day or 2, right? We are far faster than the rover in the moment, but we were not designed as an operational asset, right? So our operations tools, the flight software on board, none of it is geared around kind of long duration, long distance traverses and sort of normal stuff that you would do, right? We were designed to do a test flight and then carefully review the data on the ground. And so in practice, it's very difficult for us to execute more than a flight every couple of days. And when you take that into account, whereas the rover was geared to put down distance, and we were geared to carefully fly once a week, maybe, then the operational cadence is different. And so even though we're faster, the rover can actually outpace us in most cases. This was particularly true in the early part of the mission because we had sort of very carefully tested the flight envelope, right? We're testing the waters. It's like walking into a swimming pool. You're like in the 3-foot zone and you kind of go into the 4-foot zone. You're like, okay, this is still safe, right? And so at this point in the mission, our maximum speeds, our maximum flight times, our maximum altitudes were not enough to really get the most out of the helicopter because we just hadn't tested those environments, those sections of the flight limit, right? Later on, and we'll get to it, we expanded that significantly, and that would give us a better competitive ability to keep up with the rover. But at least at this point, it wasn't possible. And so if you go back to that map, you'll see the solution was, hey, we're gonna cheat. We're gonna cut across Zeta. So you see, yeah, we sort of shortcut the rover's path. The rover didn't want to go that way because there's all sorts of gnarly terrain. There's these, sand ripples and gnarly stuff there. So the rover didn't want to go there, but we were able to find enough kind of safe landing spots spaced throughout that region to go across. And actually, that is when we set the longest flight record for Ingenuity. We were 700 plus meters. And that's when we sort of were running across Zeta. Yeah.
I'm just looking at long flights there.
Flight 25.
Flight 25? Yeah, there you go. That's Flight 25, that one long hop.
Yep. And later we actually got the ability to do better than that, but then the terrain prevented us from doing these. And we can talk about the technical reasons there. But yeah, so we cut across Zeta and then, yeah, we sort of intersected with the rover, right where the yellow and the white intersect. I think Flight 28. Yeah, that's right. So that was the last flight before we browned out. So it's entirely possible the mission could have ended there. Winter was coming, well, to be technical, fall was coming and the dust storm season was coming, which happens kind of, Mars is a 2-year calendar, roughly one Martian year is more or less equivalent to 2 Earth years. So all the seasons are twice as long. So there's roughly 6-month seasons. They're actually, the fall and the winter are actually a little bit shorter. The spring and summer are slightly longer.
That's helpful for your testing though too, right? Because
We'll
if you ideally want spring, you've got twice the amount of spring to test stuff.
It's lucky. Yeah, Mars has an elliptical orbit. And so the northern hemisphere gets these great long balmy summers and springs and these short but mild winters. And the southern hemisphere just gets hammered because it's further away and tilted away during winter. And anyway, but we can talk about weather if you want. But anyway, yeah, so that's where we browned out right there. The dust storms came, they occluded the sun, and we browned out. And then you can see after that, after Flight 28, if you start moving to the west, all these flights are really short, right? Like itty bitty little hops, 100 meters if you're lucky, right? And that's because we were in this mode where we're waking up in the morning, having completely browned out, more or less depleted the battery, just trying to stay warm at night. And then the energy we had available for flights was only what we could harvest in that day, right? So we would sort of wait all through the morning and the afternoon, and then late at the afternoon when our power hit the max, then we'd fire off a flight. And even then we were lucky to get like 100 meters, right? And so you can see that we were sort of just barely limping along. And this was the point where it was like, if the rover had decided to go someplace, there wouldn't have been a way for us to keep up. And the mission would have been ended there as well. As it turns out, we kind of lucked out, and the rover needed to do a little bit more science. You can see far to the left there where they grabbed a few more sample tubes, those little red indicators. Yeah, so they needed to do some science, and then they needed to drop off sample tubes. So the Perseverance mission, their main mission mandate is to go collect the necessary geologic samples they need to answer the questions that they were designed to answer, and then get those back to Earth. Or deposit them in a place that they can then be transported back to Earth, so that we can do the analysis and answer the big questions, right? And so Perseverance carries way more sample tubes than they need to do that, to answer those questions. And so the first year of the mission, roughly, they collected the bare minimum necessary samples, and then they deposited them there in kind of the middle in that flat area. Yeah, exactly. Right in that region. And that is called the Three Forks Sample Depot. So this was meant as a contingency deposit of samples. These are the, like I said, they're the bare minimum sort of that you would need to answer the questions. But from a geology standpoint, they're not the best, right? Obviously, with years more of mission ahead of them, they're likely to find better stuff. So anyway, they deposited these samples. And this whole process of taking a few more samples to the west and then coming back and depositing the samples and making sure they were properly placed on the surface for later pickup, it actually took a long time. It took the better part of winter. And by the time they were done with this, it just so happened that we were coming back into spring on Mars year 2. And so we got really lucky because right at the moment when they decided, okay, we're done, we're getting out of here, that happened to be the moment where the sun came back and our power story improved, and you can see right away that our flights expand. We also did a flight software update that made us a little bit safer on landing, so we were able to find safer landing sites and be a little bit more aggressive in flight planning, and all of that came together right at the moment, right as we were coming out of winter, sort of in the first spring there, or the second spring, sorry. And that's when we started racing up the delta. And if you go back to that map, you can see that we had been enjoying this nice flat crater floor. That is Jezero Crater. And then there's this big delta, this water delta, where the rivers emptied out into the crater. And you can see that if you zoom out a little bit, you can see that kind of fan shape. So that is a river that's, just emptying into the crater. And right there in the second spring, that's when they started making the trek up the crater, or up the delta. So it all came together, thankfully. Now, it turned out to be a lot harder than we thought, because as soon as we went up into that rocky stuff, we ran into other challenges that we hadn't run into before in the previous part of the mission, which was that if you've ever taken a radio up into the mountains, you start losing line of sight, that it doesn't take much to block your transmissions. And so we were compelled, because of the telecom environment, to stay pretty close to the rover. And it was kind of a nail-biting time, because we had to stay close, but not too close, because we're not allowed to be close enough to endanger the rover should something go wrong. And we have to be pretty selective about where we're landing, and we have to make sure that we're staying within telecom of the rover. And then the rover is just sitting there booking up the delta, right? So we're sitting here like doing these tiny little hops to try to stay in that Goldilocks zone.
Wait for me. Yeah.
Yeah, it was nerve-wracking. Yeah, but actually that's during that period of time is when we set our kind of flight cadence record. We managed to pull off 4 flights in a 10-sol period, which is, compared to our early mission performance of once per week, is just astronomical.
Yeah.
Right?
Hey, there's a question from chat that's sort of relevant to what we're talking about now. What was the range that the helicopter could communicate with the rover? Like you said, there's sort of a rover keep out zone because you don't want the helicopter to crash into the rover, so you had to say a difference away. But if you're too far away, then you can't keep up the telecom range or the radio signals or whatever, right? What was the range that you were operating in? Was it like 100 yards or 100 meters, or how far was it?
Yeah, so we've tested the radio. So down when we were in the Jezero crater, down at the bottom of the crater where it's wide open spaces, we've tested it past 1 kilometer.
Okay.
Right? So we're not that tethered to the rover in those benign terrains. But as soon as you get up into a place like the Delta, where you've got rocks and cliffs and it's really gnarly terrain, it could be 100 meters, right? And the keep out zone around the rover is 45 meters. So you're like right there in that little sliver, potentially, right? And in fact, in many cases, we would intentionally fly out of telecom range as a way to kind of relax that constraint a bit. And that worked a lot of times. And it didn't work very well one very significant time. and we can talk about that in a minute if you want.
Okay.
Um,
Well, let me see if I can illustrate that real quick, because there is a scale on the map here, right? And down in the lower left-hand corner, you can see there's about 100 meters. So there are definitely spots throughout here, right, where I don't know exactly when this was happening, but if the rover is somewhere up here, you had to be more than a kilometer away from the rover at places, right? Am I reading that right?
That's right. Yeah, that's like I said, out past a kilometer is where we've tested. I don't know the exact number, but
yeah,
kilometer plus for sure.
But this is like nice flat crater, I guess, bottom where you have line of sight, and you can get a lot better signal if you're just line of sight looking right at the rover versus, okay, now it's over a hill or down in a valley or whatever, then your range is a lot shorter, right?
And it's topographically flat, which actually matters because the antenna on Ingenuity, it's an omnidirectional antenna. But its radiation pattern essentially is a plane, right? So if you're sitting on a giant plane, you're sitting right in kind of the sweet spot of the antenna. As soon as you start having differences of elevation or tilt and that sort of stuff, you start losing signal strength real fast. So that hurts you in addition to the line of sight issues.
This goes into, have you ever been standing right next to a cell phone tower and you're like, I don't have any signal, there's a tower right there.
It's above me.
It doesn't aim at the ground, it aims in a real long pattern to get a wide area. And if you're right below it, the antennas are firing above you. The antennas are not pointed at you, they're pointed off into the distance, right?
Exactly.
And that's like, here, let me see if I can draw that real quick. I can get a helicopter up here. Here's a helicopter, right? And so when it's transmitting, I'm not going to be able to draw the lobes correctly, but it's not transmitting like this, right? If you transmit like that, you're wasting a bunch of power transmitting into space and transmitting point blank into the ground, right? You design these antennas so they're transmitting sort of like this and like that. So it's an omni antenna, 360 degrees, right?
Yep.
But you don't want a really wide beam pattern because any signal you're sending that's not going to go towards the target is just wasted energy. You're radiating wasted watts, basically, right? Is this kind of close to how thin it is, or is it a lot thicker than this?
Yeah, no, that's roughly correct. It's a monopole antenna sticking out of the top of the solar panel.
Yeah.
So yeah, it's going to have these big, wide, sideways lobes. Yeah, you can almost see it.
Kind of see, yeah.
You can see it there. It's to the left of the rock and down.
Is it this one or the darker one in the middle?
It's floating there, and you can see a little white zigzag.
Oh, there it is up there.
Nope.
Also not.
Are like rocks and dust, right?
Yep, that's the one.
So I actually wanted to ask about that too. So you mentioned dust storms, right? I would assume that would maybe also affect like the way it transmits. If there's like a big dust storm, maybe it's not as clear to be able to send the signal and whatnot. But also, like prior to all of that, prior to the brownout and whatnot, you guys, yes, you were testing, the ability of it to fly, to hop, to move. But you also had a dust storm earlier on too, right? Where you had to figure out how to kind of like shake it off a little bit.
I'm not sure that we ever. Well, okay, so I think I know what you're talking about. John, can you go back to the drop off pic?
Yes.
So right after we got dropped off. So during landing, there was a bunch of, there's always rocket plumes and dust and sand that's kicked up during landing. And you try to protect everything from that, but you don't always succeed. And if you zoom in on the solar panel, you see that there's like a whole bunch of dust and sandy stuff that was deposited on our solar panel.
There's the antenna.
So that was the first kick in the gut, right? When we first landed, because we knew power was going to be an issue from day one. We were like sitting there counting joules. Okay, can we stay warm? Are we going to be able to fly? And now here, right out of the gate, the rover deployment mechanism on the belly pan had accumulated some of this EDL debris and then dropped it on our solar panel when we were being deployed.
Oh, jeez.
Right. So that was really unfortunate. And thankfully, after it was like it took probably 1 or 2 flights to shake it off. But that dust that's on there is like a fundamentally different kind of dust than what you get kind of lofted in the Mars atmosphere, right? So there's the stuff that's in the Mars atmosphere is very, very, very fine. And it stays hazy for weeks, right? And when it deposits in this very, very thin, sort of almost electrostatically coated layer. Actually, that is... we don't 100% understand the dust story on Mars, but it is likely that it's electrostatically coating things, okay? And this dust you might call it sand or debris. This was kicked up by a rocket plume, right? So it's much thicker, coarser, and actually, as it turns out, much easier to mobilize on Mars and much easier to clean. So we cleaned that off, in the first couple of flights. But when the winter hit and the dust storm season hit, we got exposed to something that was way more insidious, which is this atmospheric dust that was kind of coating the solar panel in a more uniform way. And if you go to the picture 776, Sol 776, this was kind of the first good imagery we got from the rover after winter started. You can see that like we are just completely caked. You can't see the solar panels, the solar cells anymore at all. Yeah, I mean, look at that.
Yep.
It's totally caked.
It's just a layer of dust.
And what's even crazier is the rotors. If you look at the rotors, they're also caked with dust.
Yep.
Right?
Yeah.
And these things are spinning at 2,500 RPM, 2,800 RPM, depending on the season. And they've got dust on them. How does that work, right? So this is the craziness of Martian dust. It is very tenacious. It sticks to things. And so when we saw this, when we saw that the rotors were covered, we kind of lost hope of any kind of active cleaning approach. Actually, there's been very few successful solar panel cleaning approaches that have worked on Mars. We've flown, it's now been decades of operating on Mars, right? We had Pathfinder and the MER rovers, and we had InSight and all of these, right? A lot of solar powered missions. And we haven't really ever had successful dust cleaning. Now, one of the reasons for that is that we never try, to be honest, when we're designing these missions, we don't have the scope or the budget or the intent to make it capable of self-cleaning, right? Because you can't justify that for a 30-day or 90-day mission.
Yep.
And so just from a project management standpoint, we never spend money on dust cleaning approaches. But once we're there and we're on year 10,
Like,
right?
I wish we would have.
It would be nice if we had put in some dust cleaning, but it doesn't stop us from trying, right? So the MER rovers, what they would do is they would actually go park kind of in the leeward side of sand dunes, and the sand would come off the sand dune. It would sandblast the panels. And InSight, they actually dumped sand on their panel because the wind would carry the sand and sandblast the panel. It's really counterintuitive, but the sand is way easier to mobilize than this electrostatic dust.
That's brilliant.
It's using the sand as a brush because the larger particles are easier to. When you say mobilize, you mean move, right? It's easier for the forces existing in the environment to move those around, and they like scrub it off because you push the big particles and it moves the little particles off. That's cool.
There's this great GIF or video, whatever you want to. I forget, but it's a series of images from InSight where they show, okay, we're sitting here, we're dropping, and then you see the panel sort of have this blast pattern on the panel from where they had scoured it off. At any rate, I mean, one thing we have that no other mission had is the ability to fly and enormously impact the aerodynamic environment around us, right? We get hundreds of meters per second of air kind of flowing around us.
Yeah.
And so we thought maybe, if we vibrated as we're flying, or maybe if we flew really, really fast, we could blow the dust off. That's like the standard Earth intuition, right? Sure. But I think this picture shows that it's going to be tough to fly fast enough to clean the dust off. We actually, we did the math, and we know roughly how fast it will be, how fast we would need to fly, and we know Ingenuity can't do it.
Right.
So
and
maybe on future helicopters, we'll give it a try.
And that, kids, is why in The Martian, when it blows over the Mars ascent vehicle, anyways, it's tough. Like the atmosphere of Mars being very, very thin. You can, like you talked about at the beginning, you had to have larger blades, and the rotation of the blades had to be faster. And could you actually fly in that environment was a question you started with. But it's not like just get a Martian leaf blower and just blow on it. It's fine. Why don't we install that on the rover's robotic arm, right? It doesn't work that way.
I mean, ironically, the rover does have a dust removal system on its arm. It has the GDRT, or the GDRT, that is specifically designed to remove dust. It has a big tank of high pressure nitrogen, and it can go and puff on things. So that conversation did happen at some point where we're like, hey, rover, you want to spend some of your precious propellant to come blow our panels off.
You dumped it on us. It's your fault. You dumped this stuff on us. Come blow the panels off.
Yeah.
But as you can imagine, that was a non-starter. By this point in the mission, we were largely on our own. The rover had a mission to do, and they didn't want to have any more interference from the helicopter. And so basically, we were in a mode of just staying out of the way and trying not to inconvenience them.
Yeah, I could imagine like a cartoon of the rover going along doing its science, its super important science, and the helicopter being like, hey, me, hey, take me along, I'm here too. Like I could be useful. Look, I'll look over this ridge for you. Hey, check it out. You know what I mean? Like that sort of interaction between the two. The rover's over there like, oh my gosh, the helicopter again.
And I think right around this time, it was in the Sols in the 600s, somewhere in that, about the time we got this picture. There was also a big issue because the GDRT was having issues, and they were noticing that they were burning through propellant way faster than they thought they should. So it was not a good time to bring this up. But suffice it to say, we continued without having solar panel cleaning from the rover.
There's the keep out zone where you're not allowed. I don't know if keep out zone is the right thing. I guess that's what we sort of call it with rockets and stuff like that, right? Where the helicopter's not supposed to fly so close to the rover because if something goes wrong with the helicopter, you don't want it to endanger the rover. Was there ever a conversation about having the rover or the helicopter try to blow dust off of the rover's solar panels? Is that just a non-starter, or did anybody ever say, well, what if?
So, I mean, so Perseverance is nuclear powered, right? So actually, they don't care about
They don't care.
Or they don't care about
okay.
Power. They like winter came, they're just trucking through, no problems at all, right? In many ways, the rover is much more kind of insensitive to the environmental conditions on Mars
than the helicopter.
Okay. Right? For that reason, and so they don't care so much about the dust. The dust, for them, it's a nuisance. It might get on their cameras potentially, but even that's been sort of well protected in the design. So, they really didn't care. And any notion of us flying near the rover would be met with extreme skepticism. And so, that's why the keep out zone exists, because you never want this like scrappy little tech demo helicopter to come in and torpedo your $2 billion rover.
Yeah.
The optics for that would be abysmal. So
there's no like requesting a flyby of the rover, like Top Gun style or anything like that. That's not a thing. No buzzing the tower.
No, we would all be out of a job.
Yeah. No reason to blow the dust off the RTG or anything like that either. Another question I've seen scroll by in chat, because chat has so many questions, I can't keep up with all of them. Were there any studies or conversations about electrostatically trying to repel the dust off of solar panels? Like I've heard of that with the moon, but I've never heard of it with Mars.
We have the technology.
Yeah.
So NASA's developed it, right? That's what I say earlier. It's an administrative hurdle, not a technical hurdle.
Yeah.
So there's a group at Kennedy who's developed what's called the electrostatic dust shield, or EDS. And it's actually remarkably simple. You put a couple high voltage wires kind of over whatever surface you're trying to protect.
Yeah.
And you can literally sit there and you can cause the dust to sort of dance off the surface by cyclically charging and discharging the surface. And it works phenomenally well. You can use it for camera lenses, solar panels. I mean, they've got it more or less ready to fly and have it very mature. I don't know that it's been actually flown on any mission yet, but it looks really, really promising. So we have the technology. We definitely could have. You can imagine on a helicopter like Ingenuity, where we're literally counting every fraction of a gram, something like that for a 30-day mission would be impossible to justify on an engineering basis, let alone a cost basis.
Right.
Right.
Well, one day JPL is just going to have to admit that when they say they're going to do a 30-day mission, 1,000 days later it's still going. Like somebody's just going to have to own up to that at some point.
You guys are just too good.
They're too good.
It's an artifact. It's a natural artifact of designing missions that succeed, right? If you want to be sure this thing's going to work for 30 days, you've got to do a lot of engineering. You got to be 110% sure on everything, right? And if you happen to get lucky and you make it past that 30 days, well, suddenly all of that engineering pays off and results in a very long-lasting vehicle, right? Because you've covered every base, you've accounted for every obstacle, because you want to make sure it works for that 30 days. So I don't know that you're never going to get somebody coming and saying, oh, this thing's going to work for 10 years.
Right.
There's too much that can go wrong.
Then you're on the hook. Like, oh, you said 10 years.
So like even Perseverance, right? So it's Perseverance, it took them an entire year to complete their base mission of taking the samples and dropping that contingency sample cache, right? Even that was stressful, I think, for a lot of the rover designers because the previous rovers had been specifically designed. The MER rovers, Curiosity, not Curiosity, Spirit and Opportunity, they were 90 days. I mean, 90 days, it's a very short mission. You can design almost anything to work for 90 days, right? But 10 years or several years, now that's really a different challenge.
Yeah.
So yeah, it's just how it is. It's kind of a natural consequence of how we work.
JPL is going to have to change their. Oh, go ahead, Elysia. Go.
No, just speaking of having to pack so much into such a very lightweight, tiny package, especially as like a demo, though. Like, did you still, even though you were like, okay, we can't build in this electrostatic repelling thing or like brush cleaners or something like that, did you still think about building in some sort of redundancy for if there's like a very essential motor that breaks or something like that? Were there any other extra things that you packed in just in case?
Yeah, I would say for the most part, Ingenuity is what we call a single string failure system. Okay, most spacecraft, especially high budget spacecraft that must work, that have to succeed, have redundancy at lots of different levels, right? Ingenuity, I think first of all, we're what's called a Class D mission, that is like kind of a higher risk, lower cost,
Right.
lower expectation class, right? So most of the flagship missions are Class B, human space flight's Class A, right? So we were way low on the sort of need to succeed and tolerance for risk. So anyway, there was an acknowledgement early on that if we lost a motor, we're toast, right?
Right.
You lose a rotor motor, the physics don't close anymore, you're toast. You lose a servo motor, in all likelihood, your swash plate's going to be broken, you're toast. And so just because of the sort of the posture of Ingenuity being high risk, high reward, we were able to accept that. Now, there is, you could argue, some redundancy in the fact that we have dual swash plates. So Ingenuity early on went through a couple different iterations. As you guys know, it's a coaxial helicopter. We also looked at kind of traditional helicopter with tail rotor. But when we settled on the coaxial design, that is two counter-rotating blades, there was a thought, well, hey, you could power these both with the same motor. The same drive motor could power both. And you could also use the same collective. If anyone's familiar with helicopters, there's essentially three control knobs you have, which is there's cyclic, which is left, right, forward, back. There's collective, which is kind of changes the blade pitch all around the blade circle and gives you up, down. And then there's, rotor speed, right? So you've got a couple different knobs. And so early on, some of the earlier demos actually, they combined the collective and they combined the rotor motors for the blades, because the blades being counter-rotating, they always need to cancel the torque from the other blade. So the speed and the collective settings need to be essentially identical at all times. Otherwise, the helicopter's going to
it'll rotate one way or the other. Yeah.
Yeah. So that was the original plan, is actually to have two. And you could do other things too. Like you could, let me finish my thought. The original plan was to have two blades, but a single motor, right? And to somehow link the collectives or the cyclics. One of the most promising plans was actually to have one blade that was just essentially dumb, right? No machinery at all, just providing thrust. And then you've got cyclic and collective on the other blades that give you, your pitching and rolling and your yawing from changing the collective. But so we opted for a fully redundant swash plate system. And so I think that's like the only redundancy you could say we really have. And that was done more for kind of vehicle trimming and tuning standpoint. Like, what if we got on Mars and we found that we had this, really nasty yaw moment because the blades weren't balanced aerodynamically or something like that, right? Having all 6 degrees of control here, having left, right, cyclic, forward, back, cyclic, and collective on both rotors allows you to go in with software and tune it and trim the aircraft. Now, it turns out we didn't have to do that. Like, the work we did in the test chamber here in JPL was enough that the helicopter largely flew exactly as it did in the chamber. And those settings, even to this day, if you go in the software and you look at the settings, like the collective settings and the cyclic and settings, they're all essentially set to the same thing. When we do pitching and rolling and yawing, we're commanding exactly the same thing to both upper and lower blade.
Yep. And y'all, just real quick. Yeah, quick. What we're talking about here, for everybody who looks at this on the screen and like, what is this? Like the world's worst Christmas tree? This is the complicated part of the helicopter that controls how it flies, right? And what Travis is talking about is the fact that you have this assembly here, and that's a doubling of this assembly here, as opposed to, just cancel all this out and have a dumb blade that just turns, or maybe it has a physical balance like a fly bar or something to keep it sort of flying, and then you have all this complicated stuff down here. The design you went with, which is the design we have here, has these sort of two copies of the things, one specific to each blade. Did I get that sort of right?
Yeah. I guess I should probably introduce it a little bit. So, yeah, just if you look at the blades, so they're the black things, obviously.
Yep.
And then there's these little white connecting linkages that connect the blade pitch. So if you go, there's like a little screw. Yep, that guy. So that actually changes the pitch of the blade as it's rotating.
That goes up and down like that, right?
Yeah.
Yep.
And so that is connected to the swash plate, which is that kind of cylindrical aluminum thing. And so that swash plate is essentially it's just a bearing system, so that the blade part can change, and you can control the bottom part as well. So essentially those three servo motors you see just below the swash plate, they're controlling the lower half of the swash plate. And then the swash plate's rotating, and then the blades are being controlled by the upper half of the swash plate. So this is a way to allow you to change the pitch of the blades without actually having your servos rotate, right? So it's a way of transmitting that mechanical control through a rotating coupling.
Yeah, like
and what are the little spiky parts coming out on the blade?
The nubbins.
Yeah, what are those?
Yeah, everybody always asks about these. They're very obvious and very funny looking. Those are actually dynamic balance weights, okay? So if you've ever, there's something called the tennis racket effect, which some of your viewers may be familiar with. But if you ever take a tennis racket and you flip it up in the air, as if you ever do that, you'll notice that it's actually not stable in this rotational plane. It'll actually want to flip.
Right.
Okay. And so when you've got these blades spinning, they're actually getting that same effect, right? So they're essentially tennis rackets rotating around on the helicopter. And so the tennis racket effect will naturally cause the blades to flip off, right? It'll cause them to have pitching moments. And so if you don't do anything about that, then the poor little servos are sitting here down, like fighting that the whole time. And that means your servos are burning more power. They have to be stronger. They're working harder. They're going to wear out quicker. And so all you have to do to get rid of the tennis racket effect is you just have to change the mass distribution of the blade so that it doesn't have this strong sort of flat planar mass distribution. And so you need to get some mass kind of off that plane. And so that's what those dynamic weights are doing. There's like a little ball, a little mass, a little metal ball at the tip of that weight. And its whole purpose is just to get the weight off the plane so that the servos don't have to work so hard.
Huh. Well, now did anybody in chat know that? I'm going to ask.
You do see these. You will see these on like really tiny like toy helicopters sometimes because they're dealing with the same thing, right? We've got tiny itty bitty servos that are having to work really hard, and so it is sometimes something you see. You don't see it in full size helicopters generally because they have massive
beefier,
beefy control authority. So yeah, it's sometimes something you see on helicopters.
How big are, so these are the servos, right? These two servos down here, like there's a servo and there's a servo. Is that like the size of my pinky, or is that a lot bigger than I think, or how? I have no context of how big this is.
Those are DCX 10s. They're 10 millimeter in diameter. So
okay,
centimeter.
That's that's small. Yeah, that's pretty small.
Pinky size is about right.
Yeah. As I was looking for something, and I'm like, well, now I'm going to measure my pinky and see if it's a 10
that huge drive motor, the big black cylinder right below the servos.
Yep.
That's the main motor for the rotor. It's very powerful, by the way. It's like 150, 200 watt motor.
No kidding.
Only this big. So It's just to give you a sense for scale.
Yeah,
right?
yeah.
It's all pretty tiny.
So these are like these two black parts here, and I digress because at one point in my life a long time ago I wasted some money on RC helicopters, which is one reason that 72 flights on Mars, I couldn't even do one flight in my living room without wasting a bunch more money. So I'm really impressed with this. These are the motors right here, right? Those two bits?
Yeah, that's right.
And I would assume that the top motor drives the top, and they're sort of driving down like that, right?
Yep.
Okay, and then this
That's right.
assembly here is controlling the blade above it, and there's another assembly below controlling the blade above it. So this whole set here, I guess, the motor, the blades, and then the swash plate and servos and assembly, like that's that one unit of the helicopter, right?
Yeah.
Yeah.
Actually, that's really nice from an engineering standpoint because you only have to engineer one and just build 2 copies.
There you go.
Yeah, but yeah, you got it.
Yeah, and real quick, folks, when we said the counter-rotating, like y'all all know the traditional helicopter. Let me go back to a picture of, here we go. Well, that's not really a traditional helicopter picture, but what is Ingenuity missing, right? It's missing this part that is like the tail with the little blade on it like that, right? And it doesn't need that because it's got 2 blades right here. And what's going on is one of these blades is going one direction, the other blade is, well, that's not the other direction. One of the blades is going the opposite direction, and so they cancel out. Like if a helicopter didn't have this part and it just had one blade, the helicopter would just spin. If you ever seen a movie where the tail gets shot off or something, right? An action movie. But when you have 2 blades like that are counter-rotating, you don't need the little tail part, and that's why all that machinery in there is so important, because the blades are canceling each other out. But then exactly how the pitch of the blade is, which part of the spin around the edge, like that's how you control where the helicopter goes. Because otherwise you just go up and down, and that's all you could do unless you can change the geometry of the rest of the blades. Anyways, I think it's really
absolutely correct. I mean,
I wanted to draw a helicopter tail.
There's an enormous amount of torque generated by shoving that blade through the air, right?
Yep.
And that torque has to go somewhere, right?
Yep.
So you've got to counteract it somehow. So traditional helicopters use a tail rotor. It's got pros and cons, right? The tail rotor is not really doing any useful work for you, right?
Yep.
It's like its whole purpose is just sitting there beating the air behind you to provide that static torque. So in some sense, it's kind of wasted energy, right?
Yep.
Coax is nice because you're getting useful work out of the counter rotation torque, right? The upper rotor's torque has got to be counteracted by the lower rotor. Well, the lower rotor is also producing lift. So it has this nice efficiency aspect. Now, there's crosstalk between the blades, and aerodynamically, it's a little messy. And so it can be good, it can be bad. We do coaxial helicopters here on Earth, actually. Not super common, but like some of the Russian military helicopters are coax. It is a design that we do here on Earth, but in this case, it's primarily driven by packaging, right? This thing's got to ship in the UPS box on the belly of
the belly of the rover.
Perseverance rover, right? So if you have a huge tail rotor sticking out, now you've got to find some way to package that thing, right? Well, you've got to package the main rotor anyway, so why not just package 2 main rotors?
Just 2 main rotors, yeah.
Yeah, so Ingenuity's design is like 50% driven by physics, 50% driven by just trying to get this thing to cram into a small box.
The IKEA flat pack that you would fit underneath the belly of the rover, huh?
Yeah, like those legs, the legs completely like hyperextend into this horrible, unnatural looking angle when it's stowed.
And I think that the scale of this, like if people don't realize like the scale of everything, we actually had, I don't know if you saw it, Dust, I just dropped it in the thing. If you can see, I can grab it. We actually had a full scale model of the Perseverance rover and Ingenuity helicopter 2 years ago at the Intrepid. It was the Mars Roadshow thing that you guys had. And the size of Perseverance is like the size of a car. And Ingenuity is, I don't know, I guess how would, there's a picture of me like next to it. It's like what, like the size of like a toaster maybe next to it.
Well,
like,
I mean, so the
there's definitely a picture.
Yeah, no, I just dropped that. I was just looking for it because I thought it's to understand the scale of how big this thing is and how tiny these pieces are too for the rotor blades and everything and the servos.
I mean, for the packaging engineers, it definitely wasn't tiny. If you look at the size of those blades, they are, almost 2 meters in diameter. They're enormous, right? So you've got to package those onto the rover, and the rover may be car size, but still, like fitting that huge thing is not easy.
All right.
The avionics box is about this big, right? So it's maybe soccer ball size or a little bit smaller. But yeah, I mean, it's small, but then if you see it next to you, you're like, wow, this is the largest helicopter. Like it's RC helicopter size, I guess. You know, some of those old school gas powered RC
Yeah, the
helicopters,
bigger ones. Yeah.
it's roughly that size. It's not like modern quadrotor or hexacopter or drone size. You know, it's a little bit bigger.
No kidding.
Yeah.
We
Actually, that reminds me, I did want to finish off by saying that, so you can do coax helicopters, right? You can do tail rotor helicopters, but you can also do multicopters like quadrotors and hexacopters, right? Yep. Those do the same thing where they have counter rotating blades, and that's how they, you know, balance the torque. And we may actually go in that direction on future helicopters on Mars, for a variety of reasons, but you know, packaging probably is one of the main ones.
Yeah, yeah.
And you know, if you want to build a full-size helicopter, the blade just keeps getting bigger and bigger, right? And so if you want to fit this thing in an aeroshell to get it down on the surface of Mars, having the ability to kind of fold a bunch of little rotors actually turns out to be much easier.
Yeah, yeah. Like I want to keep talking about helicopters, but we still have so much imagery that we haven't talked about. This shouldn't just be helicopter show like 101, because there's so many interesting ways that things work, especially when you get a quad.
Don't ask an engineer about, you know, engineering.
No, but the whole point is we want to ask the engineer about engineering on the show here. Anyways, let me go through here. Chat is now debating the differences between quadcopters and counter. So if you have a quadcopter, it can be multi-rotor, but it's not coaxial, right? Like you have multiple rotors, but they're not necessarily stacked up.
You can have a quadrotor. You can have an octocopter that is 4 rotor spars with 4 sets of coaxial blades.
Yep.
That is a design too, and we've looked at that.
We're gonna have to look at that as
everything under the sun.
Yep. Let's see here. Everybody's talking about this. And by the way, folks, I still see some of these donations for Intrepid's museums programs. I see them coming in. Thank y'all for doing this. We're going to keep talking about helicopters. What else? We've gone through 66% of the show so far. We have 30 minutes left. Travis, you sent us so many different things. What do you want to talk about next?
Well, I want to talk about
Elysia wants to talk about something.
Can we talk about the crash? Because that's like the big thing, right? Like what happened? Everyone wants to know what happened. Tell us about the blade. Tell us about that picture. Tell us about what happened.
But let's table that for just 5 minutes. Okay. So we walked the audience
through
our shooter. Let's just get them let's connect the dots here.
Okay.
From right. So if we could bring up that map again. Okay, so where we left off. So winter was thawing, spring was coming, and then we started racing up this delta, right? And as I said, we got kind of lucky that we suddenly had the power to be able to do that. But it was also really stressful and difficult, right? Because we're sitting here having to so carefully coordinate our motions with the rover and not having a whole lot of margin to get ahead and that sort of thing. So at this point, we were still kind of in operational demo mode. We were trying to act primarily as scouts for the rover. So that like the first half of the mission, that was really the focus. Like, what can we do to scout for the rover, right? And so you get these epic pictures, like when we scouted the back shell. I think you have that picture.
I do.
That was coming out of the SETA traverse, right? So we snapped this beautiful picture. Like for the EDL guys, the engineers, I guess this is not science technically, but the guys that designed the EDL hardware, this was the first time they had ever been able to see what their hardware looks like after it had done its suicidal flyaway, right? So this was an epic shot for them. You get to see, what broke, what didn't.
Yeah.
Anyway, long story short, that had been our focus. After the first 30 sols of tech demo where we kind of pushed the envelope, we really were focusing on like, what can we do? Like, what images can we take? What scouting can we do for you guys? Blah, 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 right? And we were still in that mode when we started heading up the crater delta. And so you get some pretty cool shots, like for instance, Rocky Top. If you go, so this was an area where the rover, we have high resolution imagery from satellite, from the high-res camera. And the rover is using that data to plan, but they weren't really sure, like, what are we going to face when we go up here? They had kind of done a little toe dip up here, and the terrain had been way sketchier than they thought it was.
Yeah.
And so a lot of the rover planners were getting really concerned. And so this is one of those shots where we got up there and we basically did an out and back. We went out, we scouted the terrain, and then we came back. And then the next one, if you go to the next image, you'll see that on the subsequent flight, we actually went to the top of Rocky Top, and we're like, hey guys, it's pretty nice up here. Don't worry. And so like this was kind of the mode we were in, right? So then we started heading up the Delta, and we took a bunch of shots, of key science targets along the way. There were things like, I don't think I have any pictures of it, but go to the sunset picture.
Yeah, I got it.
So this was along those lines, right? It's us essentially shooting the camera in different directions, trying to get planning images for the science team and the rover planners. This one actually turned out to be the latest from a solar day perspective. This is the latest shot we've ever taken. And you can see why, right? The sun's so low in the sky that the glare is just like makes the image unusable. So after that, we dialed down the cinematic effects a little bit and flew a little earlier in the day to get better shots. But yeah, I mean, you can see the kind of incredible pictures we're getting out of this.
Yeah.
At any rate, that I think so that proceeded. We continued up the crater, and then we took this great shot of Belva crater that is perhaps one of my favorite pictures of all time from the helicopter mission. This guy here. So the science team was, for timeline reasons, they actually weren't going to get a shot of Belva crater. They were going to have to skip it because they had to kind of keep on schedule, and they were going to cut it out. And so we're like, hey, this is something we can do. So we got up and we took this shot of Belva crater. So you can see Belva crater in the background, and we got a lot more than we bargained for. Actually, we got the rover there on the left of the frame. We got rover tracks going across the image.
Did I trace the crater correctly, or is it much wider than that?
I think it might go a little further to the right.
To the right, yeah, like this sort of deal.
Yeah, that might be it roughly.
Yeah, something like that.
And I need to give a shout out here to Simeon Schmaus. He's very active on Twitter, and he has a habit of taking our images and working his photographic magic on them to make them even better. I have the original for this image.
Yeah.
It's just not quite as nice as the Simeon Schmaus version. So that's what I'm showing you here.
Nice.
So we actually do look at his images and frequently, talk about them in our team. So I don't know if he knows that, but if he's ever watching this, he'll find out.
There you go. Nice.
Anyway, so this is going back to kind of the timeline. So we took this epic shot of Belva crater. And then right after this, we flew out of comms range intentionally. We sort of flew back behind us because the rover was going to be hot on our tail, and we wanted to keep ahead. And so we flew essentially due west, which is, right now we're pointing east. So due west is right behind the camera. And we shot way over to the west. And right at that moment, like 2 days after we did that flight, the rover's like, you know what? Actually, we want to go north. Change of plans. They found some scientifically interesting stuff, and they actually did decide to go up and take shots of Belva crater and did a bunch of sampling. And they were gone for 2 months. We were out of telecom range for 2 months. 2 months of the mission that was gone because we had hopped just a little bit too fast in front of the rover. And so that's why I say earlier, that was an example of mostly it worked to sit there kind of hopping ahead of the rover. But in that one instance, it really backfired big time. We lost 2 of the best flying months on Mars because of that. And it's unfortunately the kind of side effect of the position we're in, being kind of subservient to the rover.
You had to talk through the rover. Like, you couldn't talk directly to the helicopter. You had to be in range of the rover. And correct me if I'm wrong.
Yeah, that's right. We don't have a direct to Earth or direct to satellite radio. We've got the data goes from Earth to the satellite to the Mars, or to the Mars rover, Mars rover to helicopter, and back again. So it's a very convoluted, circuitous data path for us. But yeah, the rover is the final link in the chain. So they drove northeast, and we flew west, and there was nothing we could do about it. We just had to wait for them to come back.
There you go.
Well, when they came back, it turns out 2 months later, we were sitting on a really interesting piece of rock. Like, we had just basically been parked for 2 months on top of this potentially scientifically, I wouldn't say groundbreaking, but very exciting piece of terrain. And so when they came back into focus, we kept doing science scouting for them.
Are those the rover tracks?
Yes,
like clearly visible in this shot. You can see that the rover, I mean, I zoomed in on the rover briefly, right? There's the rover. I hope that's our rover. If that's somebody else's rover, we need to know about it.
Looks like Wall-E from the Disney movie.
Yeah, it is. It's like Wall-E. But these tracks, you can see the tracks going right. Oops, I keep clicking on the wrong one on occasion, and I lose my place. Here we go again. You can see the rover tracks going across the entire frame. Look at this. It looks like the rover like did a little, not a donut, but it might have went up one way, then decided to drive another way. That's
we leave footprints on Mars. We absolutely do.
But I have to say, like, shots like this make me very excited because seeing the third-person view of the rover almost makes it more real for me. Right? And we get the selfie, and you take a selfie or something like that. But seeing the rover in the distance and the tracks behind it, we don't get to see that a lot of times because all the cameras are usually mounted on the rover. And having the capability of something that backs off and gets this scene of the rover and its impact, and here's some foreground. And I mean, even
it puts it in context, right?
Yeah.
I mean, it puts you a little bit more in the world.
Yep.
And I would say, actually, that's one of the things that I've loved most about working on Ingenuity is just like, mentally, I have been living on Mars for the last 2 years, right? I'm sitting there checking the weather. I'm like, oh, what's the density today? What's the sun doing? Oh, is it a dusty day? Is it a bad day? Oh, it's cold today. And like just visually, right? I'm telling the helicopter, okay, go up and take me this shot, take me this picture. And then, a couple days later, it's coming down and we're seeing stuff like this. Yeah. I will say it's not actually that easy in practice.
Oh, sure.
The GNC planning team had to pull some serious shenanigans to get this shot. Because the RTE camera is actually, because of a late breaking engineering limitation, as we were putting the helicopter together, the RTE camera is actually pointed down like 45 degrees to the point where you can't actually see the horizon. So to take a shot like this requires... Yeah, exactly. So you're sitting here like, so you'll see on, I think it's flight, whatever the flight is for this picture. If you look at the flight
772,
it's 52.
It's 772, or it's Sol 772.
Flight 51.
51. Okay.
If you look at the flight 51 flight path, everyone's like, what the heck were they doing? Why is it all zigzaggy? What is all of that? Right? That's us taking pictures.
Is that why there's like not many pictures though of the rover from Ingenuity because of the way the camera's angled?
Yeah, it's that and just the keep out.
Yeah.
Right. Well, yeah. So having being far enough away and not being able to angle it. Wow, that's crazy.
Right.
But what a great
4K
shot.
camera. It's a good 4K camera, but just when you're 100 meters away from something, you're just not going to see much. Right?
Yeah.
But this is like, this is the kind of shot you could expect of taking rover pics. But anyway,
I'm showing it at 35% right now. Like this is not full size. Like if you zoom all the way in, that's now 100% on. We're presenting it in 1080, slightly smaller because I crop it down, right? But there's so much more resolution in this picture than you can see in one of the frames right now. That's the helicopter shadow I zoomed in on, but I wanted to look real quick because we talked about this in the pre-show. There's a glow around it. Is that for real, or is that like an image processing thing or something?
Yeah, it's called an opposition effect. Essentially, the sun, the sun vector is coming down from behind you, right? And right where it hits, you get a little bit more reflectance off the surface. So this is a well-known thing. And that's, of course, also where the shadow is, right? Exactly in line with the sun.
With the sun, yeah.
So you get this little halo around the helicopter.
I've seen it on plane flights. Like if you're flying and you can look out the window and see it's a bright sunny day and no clouds, and you see the shadow of the plane, sometimes there's a halo around the shadow of the plane. And same thing's happening on Mars. Who would have thought? Well, there you go. Okay, more pictures.
Okay, so I'll keep the mission summary brief. So at this point, we had done a bunch of science and scouting, but we had found that we were really limited. And so we really shifted gears back into kind of going back to our roots as a tech demo mission. And starting, actually maybe a flight or two before this, we really started just hitting the gas on flight envelope expansion, doing additional tests like engineering work and science kind of from our own side rather than trying to be a scout for the rover.
Yeah.
I'd say, right around here, the flight, maybe flight 53 might be the last good science scouting flight that we did. After that, it's all engineering work. So we doubled our flight speed. We doubled our flight altitude. We did a whole bunch of cool wind tests, which were not, mandated by the science team on Perseverance. It was more from our own internal collaborators, where we essentially used Ingenuity as a wind sensor. So we have this flight of us kind of hovering. And so there's two pop-ups where we're just sitting there kind of holding distance. And you can see the effect of the wind on the helicopter, and you can use that to back out wind measurements. which is something that's never been done, right? Like we've got wind measurements up here in orbit, and we've got wind measurements on the surface, and there's very little in between. So
Yep.
we started doing some of our own science.
The world's coolest anemometer there. Like, I don't know if that's actually what it was, but
And we're still working on the math to like pull the wind out, because it's not easy because of all of the other kind of confounding variables. But yeah, there was that. We started setting speed records, like I said. There's, I think, flight 60 something, 62. We did an out and back, which was sort of a scout flight for the rover, but it was also a means for us to, this guy. So that area in the upper right is called Narlu Bay. That thing, the funny shape that the rover drew out. So we did a flight 62, basically flew out there to kind of get a shot of it and fly back. We also set speed records when we were doing those flights. So we really kind of worked on engineering. We went back to engineering and doing sort of our own science. And another thing we did was conjunction. So not many people know this, but well, it makes sense if you think about it. The Mars actually goes on the other side of the sun at some point, right?
Right.
And when that happens, it's really difficult to talk to Mars because you're transmitting through the sun. And so most missions will actually stand down for about 3 weeks during conjunction. And we took that opportunity. We flew into that dusty sand ripply dune looking thing there to the left, and parked ourselves there. And we sat there taking pictures of the sand moving for the entirety of conjunction.
I have that, don't I? I have that. I think it was a video. Is that the video we're looking at?
Yeah, we have a time lapse of the 3 weeks we spent in conjunction. So this is another instance of some science that we were pushing from our own side rather than service of the science team on the rover team. And if you look really closely, it's hard to see in this, but there are actually sand grains moving, and from that you can get some sense for what the wind was. This is important because rovers hate sand dunes. They never go here.
Right.
Sand dunes obviously are the places that are active from an aeolian or wind perspective, right? So they're curious and interesting from a science perspective, but rovers are like, nope. We'll never go to the sand dunes.
Don't want to go there.
And landers like InSight, you don't get a lot of choice in where you land, right? You kind of have a kilometer landing ellipse or 100-meter landing ellipse. So this is kind of cool because we are able to pinpoint, accurately place ourselves right in the interesting spot and then park there for 3 weeks and take these images. So we did a bunch of fun science, did a bunch of fun engineering, came out of conjunction, and we did one final big thing before the end of the mission, which was system identification. And so that's flights 68 and 69. And what we do there is we basically get the rover or the helicopter. Yeah, so those two out and backs.
Yep, there you go.
Those guys.
Right here.
People are probably wondering what we're doing. We couldn't do any of this stuff earlier because the terrain was really gnarly and you need a nice flat space. But essentially, on Earth, when you're testing a test vehicle, one of the very first things you do when you get it up in the air is you start checking your models, checking the performance of the aircraft, right? Basically get it up to speed and wiggle the steering wheel a little bit to see how the vehicle behaves.
Tap the brakes and
And this is something we've been wanting to do with Ingenuity for the entirety of the mission, but it was always deemed too risky, right? Because as soon as you start wiggling the steering wheel, there's a chance you could wiggle a little too hard and the thing could crash. But at this point, kind of the sense was it's time. And so we did that, and it was phenomenal. The data, we sent it up to our collaborators up at Ames, and it's going to basically be used for the next, for the design of the upcoming rover or helicopters, should there be more helicopters on Mars. And with that, we turned ourselves westward to rendezvous with the rover at Bright Angel. Bright Angel is that, I don't know if you can see it, scroll out just a little bit. Bright Angel, keep going west. Yeah, so right there, kind of where the river valley pinches off, right where the L in Vallis is a formation called Bright Angel, which has always been a science target for the rover. And the goal was we were going to head there, rendezvous with the rover, and get some nice close-up imaging to see how the helicopter had sort of held up after 3 years on the surface of Mars. And so we were starting our traverse, and rovers hate sand dunes. So you might say, well, why are you guys flying over sand dunes? Well, sand dunes are our bread and butter.
We because you can.
Because we can land in them, actually. It's because one of the things we were afraid of more than anything is landing on a rock.
Right.
Sand dunes don't have a lot of rocks. So it's a great place for us. It turned out this sand dune just happened to be a little bit more rock free than every other sand dune we've ever flown over. And so on flight 71, we got to land now, triggered an emergency landing because the state estimation system wasn't able to get enough features to sort of get a sense for where it is. On Earth, you have GPS and you have other navigational aids, and you have a variety of different ways that you maintain a sense of where you are and what your attitude is and your pitch. For us, it's primarily two things. We've got a very, very low grade IMU that sort of can keep us flying on the order of a couple seconds before its drift gets so bad that we'll crash. And then we've got a downward looking nav cam that sits there taking pictures of the surface and matching those up and looking at features, right? So it looks at how the features have changed as we fly. Well, if there aren't any features in the image, it's really hard to do that. And so, yeah, you can see this. This is actually that sand ripple field.
Yep.
It's incredibly featureless. I mean, from a human perspective, you can pick out some of the ripples and there are a few things, but our feature tracker in particular is looking for like rocks and pebbles. It doesn't actually see these linear features. So yeah, you've got a few, but not much.
Yep.
And so that actually caused Flight 71 to fail. We landed on the side of the sand dune. We came down pretty hard. We think we probably came down at about 1 meter per second lateral velocity, possibly more.
Lateral velocity, wow.
Yeah. Yeah, so if the state estimator gets confused, when it's coming down, it thinks it's coming down straight, but it can be coming in at a sort of sideways.
We've had some lunar landers that have had issues with lateral drift lately and ended up on their heads after landing. Lateral drift.
So that feature tracking, it's really tricky. And to be fair, this thing was never designed for this, right? It was we never had the budget or the time or the engineering effort to be able to design a helicopter that could operate on every surface on Mars.
Yep.
So
real quick, let me jump in real quick. We're sort of zooming in on the rocks here, right? Have y'all ever seen the green screen where they have the green screen suits on and they have the little balls velcroed or taped or whatever to them, right?
Yeah.
Yeah, and you've seen them when they're doing the CGI effects and that's how they're tracking the actors' motions. Those are the little points, and the computer is looking for those points, and if the actor wasn't wearing them, it would be much more difficult to put the CGI on top of them, right? Well, that's kind of what y'all are doing. You take these little known points, in your case rocks, since you can't go out there and put little reflective balls all over the terrain of Mars, right? You're taking those points and you're using those to sort of see how you're moving as they move across the image, right? So not exactly the same, but maybe...
I mean, it's exactly... the only difference is in green screens with the fiducials you're talking about, it's structured and pre-planned, right?
Right.
We're more opportunistic.
Right.
It's like whatever the feature tracker can pick up. In fact, if you go back to the second Rocky Top picture, like that gives you a sense for like the kind of terrain, like this is what you're normally used to dealing with on Mars, right? There's like pebbles and rocks and outcropping, like a nice, very textural surface, right? Plenty of stuff to track. But you go back to the dust, the sand dunes that we ended in, and you can see it's just totally void of anything but soft, smooth, buttery sand.
Let me see if I can do it. Like here, y'all can see the screen moving around, right? Like if you were a camera trying to navigate a helicopter, these rocks give you a lot of context as to what's happening. I don't know if this is going to work, but if I zoom in here and I just do this, we're humans, we're good at doing this. But if I do that, there's not any real clear features besides the fact that y'all can see that I'm moving it. I don't know if you see my mouse or not. Those rocks really give you context in like nice points with contrast that you can look for to help navigate the helicopter, right? Yeah, that was a bad example. I don't know. I was trying.
That's perfect. Yeah, that's exactly right. And that's exactly what happened, on Flight 71, is the nav system just couldn't keep its bearings. And it said, at some point, hey, guys, like I don't have a good nav estimate. You need to get us back on the ground. So we got an emergency landing.
Yep.
We came down and, that spooked the team quite a bit. We spent 3 weeks, I think, looking at it and trying to sort of rule out every other possible cause. And eventually we're like, okay, well, it's pretty obviously just a nav issue with these sand ripples. We need to get out of here as quickly as we can because this is dangerous terrain, right? But it's a catch-22 with Ingenuity because we don't have any global localization ability. We don't have any ability to like get in the air and figure out where we are.
Right.
We only know where we are relative to where we started. And so to fly a safe plan, or to plan a safe flight, you have to know exactly where you landed, right? And you have to know exactly which direction you're pointed because that's the starting point for the flight. And so to do that, we have to take off and we have to take a picture of where we are to localize. And so Flight 72 was a very modest flight. It was take off, spend the bare minimum amount of time in the air, and come back down, send the images down so we can plan our way out of this mess.
It's really short. You can even see right here that it's a really short flight, not a big traversal flight. Yeah.
Exactly. Yeah. So we were popping up, we were coming back down, and a couple meters above the surface, once again, the nav system got confused from lack of features. And there's some speculation here, a little bit of speculation, that we may have locked onto our shadow. Because normally the shadow is in the field of view, frequently it is. And it's not a problem because we have sophisticated outlier rejection. So we're sort of looking at all the features. All the features are moving together except the shadow. The shadows don't come in out. So you're like, that's garbage. We don't care about the shadow. We're only caring about the other features. But if your feature count gets low enough such that the shadow now looks like the only reliable thing in the screen, now you don't just have no data, you have wrong data. Right? And so we think that's what happened. And we did do things to try to help. For instance, Flight 72 was flown an entire hour earlier than Flight 71 to try to get a little bit more sun angle and more relief on the terrain, bring out a little more texture. But ultimately, it just wasn't enough, right? We were in a pickle. We did what we could, and we came down harder on Flight 72 than Flight 71. And I think most people will be familiar with the result. This was
Here's the first one.
Image we brought down after Flight 72. Of course, everyone's hearts are dropping because the blade profile doesn't look quite right. You see that in the jaggy edge on the upper left of the screen? That's the blade, and that blade shadow should be smooth. Now, it's easy to get tricked when you're looking at these cameras, that are 12 centimeters off the surface. So it could be that just you're straddling a rock or some sort of, you can see there's
it's even right there.
Exactly. So we were highly concerned, but I think we still had some hope that things were going to be okay. Well, a couple days later, we pulled down this image from the RTE. This is the high-res 4K. And of course, everyone just knew at that point that the mission was likely done.
Yeah.
You may not think about it, but the helicopters actually generate the majority of their lift from the tips of the blades. The tips are moving the fastest.
They're moving the fastest,
blade, right? That's particularly true with Ingenuity. And so with the tips clipped, we just don't have the lift to fly. Even still, I was sitting there in the meeting and I was like, no, guys, we need to verify. Maybe we could fly during certain times of the year. Maybe there's some way that we could fly.
I think everybody was doing that.
That's what I would say.
Yeah.
I mean, most people after this picture, I think most people lost hope, right? I was wanting to kind of hold out just a little bit longer, but there's the lift issue, but then there's also rotor balance.
Yep.
These rotors,
washing machine.
They're balanced with like a piece of tape, right? That's how well balanced they have to be because they're spinning so fast. So the chances of the opposite blade being broken exactly the same amount such that we would stay balanced are pretty minimal.
Yeah.
But we spent another couple of weeks sort of rotating the blades. I think if you go to the nav time lapse, you can see it. We can self-image just by rotating the blades and also taking images at different times of the day. So here we're sort of snapping shots at different hours.
Yeah, there's the rotation one.
Rotating the blades.
Yeah, sorry.
And just leave this one on for a second. It actually took us a while. We were so focused on the blade tips that we missed something pretty critical here for a little while. We caught it eventually, but you'll notice there's something funny about one of the blades. Right? If you look at the shadows, so there you go. So the first one to move, it's missing something. There's only one blade.
There's only one blade.
It's like, again, there's the shadows can play tricks with you. The camera angle is not the best. There's a lot of distortion on this camera lens, right? And so you try not to jump to conclusions, but it looked pretty unsettling. And it wasn't until a week later or so when we were finally able to get some support from the rover and they were able to take some shots with Zcam.
Yep.
And Zcam is it's got a nice telephoto lens on it. It can zoom in quite a bit. And we were able to confirm, yes, not only are all of the blades damaged, but one is actually entirely missing.
Do y'all see it in this here? Like, here's what to watch for. When it spins, they're spinning. You're spinning one, and then you're spinning the other one, right? One at a time, right? And when one moves, like sort of here's the center, here's the center of the rotor, the helicopter, whatever. In one rotation, you see something move here, and you see something move here, right? And then when the other one spins, you see something move here, but nothing is moving on the other side. There's no shadow changing on the other side. Watch it a couple times and see if y'all see that, but just that's the center of rotation, and one of them only has something moving on one side, right?
Yeah, that's right.
I wouldn't have caught it either. Like, it's just like,
I mean,
oh.
it's also really hard to see when you're looking at these in still form, because you know, that is how they're being taken. We bring them down as stills. So we're sitting there clicking through the stills, and we're like, yep, okay, blade tips, blade tips. It wasn't until we were like put it into this video that we're like, wait a minute, where is that other blade?
1, 2, 3, like
Yeah.
let's hit this.
Anyway, yeah, if you could jump forward to that, maybe the Z-cam real quick.
The Z-cam, yeah, here's the Z-cam. There we go.
So this is the shot. This is where we landed. We're sort of tilted southeast, pointed into the sun. There you go. And then there's something else. And again, this was like a mystery novel as we were piecing it together, because Z-cam, you see what looks like maybe it could be a rock there to the left of the screen. There's the helicopter.
Oh, I don't know how I just did that E, whatever. There's one too many sticks on the E. I made up for it. There's supposed to be a missing blade.
Four-bladed
Yeah, it's a
helicopter.
four-bladed helicopter E. Then over there, what's that?
Thing that's like at Z-cam resolution, it's like, it could be a rock. Looks kind of like a blade, maybe.
Oh no.
And then we got SuperCam. SuperCam is meant for doing like macro imaging, right? It's not really meant for this, but it can do really zoomed in stuff. And there you see it. That blade.
Oh.
So you can see very noticeably.
3 blades. Yeah, 3 blades.
Yeah. And then there's one on the left.
And 1 blade.
You know, actually, we had different theories about kind of the sequence of events during the crash. Originally, we had assumed it was a tip strike. That's usually what happens when helicopters have issues, and we saw the broken tips. So we're like, oh, okay, we just, hit the slope is sloped up at about 20 degrees. We had some nav error, so we just came in a little steep and just went and clipped the tips. That was the original hypothesis.
Yep.
There's no tip strike impacts here
in the image.
That you can't. So either from our imagery or from the rovers, there's no sign of a tip strike. And so the likely hypothesis now is that we just came down really hard, and the gyroscopic forces on the blades were more than they could handle. They're spinning again at like 26 plus 100 RPM. So if you suddenly touch down and you have a very big change in roll, that exerts a huge gyroscopic force on the blade.
That's the teacher on the spinny chair with the bicycle wheel, right? Y'all seen the experiments, the demonstrations where the teacher spins the wheel, then you can move yourself like this. Well, it's exerting a force, and if you don't want the force to be there, well, your carbon fiber helicopter blades might not be able to take it.
So the leading hypothesis is we snapped the blade, chucked the blade off to the west.
Like way off to the west.
And then you can see the original touchdown prints up on the sort of to the left of the helicopter.
Yep. Those these here, right here?
Yeah. So those are the original footfalls. And then once we have a blade missing, this thing is horrendously imbalanced and just washing machined itself down the dune.
And that was sort of this image here, right? Where we have that divot taken out of Mars.
Yeah, and a lot of people were like, oh, maybe that's the tip strike. How did the tip strike get under the helicopter? What's going on here? Like, because you would think the tip strike would be sort of in the upper part of the image or off to the right somewhere. You wouldn't think
tilts.
And this image is actually a little disorienting because you're pointed right now. You're sort of pointed along the sand dune, right? So the upper part of the dune is to your right, the lower part's to the left. So it's really hard to imagine like how you would tip strike there and then somehow land on your tip strike spot. So it was very confusing until we kind of started piecing things together.
Is that camera sort of looking this way, or did I draw that?
It's on that face, so that silver face that's facing toward us.
Yep, this one right here.
Yep, it's on the middle of that, pointed kind of toward us, actually.
Like in this direction, like that?
Yeah, exactly.
And it's super wide angle, which is how it can see that. It's just a really wide field of view there, right?
It doesn't see that. It doesn't see the. It sees the lower one.
It sees there's one
gash. Yeah, exactly.
down here.
Yep.
Okay.
Yep.
So those are almost like the four impact. I mean, there's probably one behind it as well where the feet came down and then it unbalanced washing machined itself a little bit as they stopped spinning. There we go. So this is inside. This is the tip of the leg, right? The tip of the landing leg.
Yep, that's the foot.
And this
Exactly.
is inside, like the feet are like this, and that's inside the foot. So.
And it's actually, well, you can see the other foot actually in the upper right, or sorry,
Just
middle right.
barely right
Just
there, right?
barely off.
Yeah,
Exactly.
yeah.
It's actually kind of a miracle that we stayed upright. And I would say it's kind of it's another one of those 110% sure it's going to work type things.
Yeah.
Where our collaborators at AeroVironment, who did a lot of the mechanical design and testing, they tested the heck out of the landing gear. They had an entire landing gear test bed where they had a mass and like landing legs, and then they just sat there dropping the thing from different heights and different, slopes and all sorts of stuff. Because, we weren't 100% sure that we could trust the nav system to put us down softly. So we needed to be able to take a hard landing, right? And so I think that's just kind of a testament to that engineering, is that even after all of that, after losing a blade on a 20-degree slope, we still somehow managed to stay upright.
Stay upright.
So here we are now, where we've been demoted from a helicopter to a lander. We're now Ingenuity Lander.
A lander, Ingenuity Lander. We're over time by 7 minutes. This is what always happens. We're like, how are we going to talk for 90 minutes? What could we possibly talk about? Then we get somebody who knows everything about something that's really cool like this, and we always run out of time, Travis.
I'm happy to stay on and answer chat questions.
Hey,
good ones.
Careful what you. What's next? Like, do we just visit it one day and we take selfies with it, or
is there any plans to retrieve it, or I mean, it's a demo, so I'm sure you guys are like, nope, that's it, goodbye. But
I mean,
what's next?
Yeah, so there's no real point in retrieving it other than sentimentality, right? It's a crashed helicopter, like so many children have found on their, Christmas Day. Once it's broken, the toy's not as fun, right? But we had intended to, we knew at some point we'd run out of money, right? Because unlike the rover, there's some limit to what we can do. We've already gone like 3,000% over what Ingenuity was designed for. We did every bit of science and every bit of engineering we could think of. And so at some point we knew the money was going to run dry, and our goal was just probably to sort of fly it up onto some sort of nice pinnacle and say, like, here's a monument to human achievement. We never got there. We will now be a monument to human achievement in the sand dunes.
Yep.
And actually, we know for a fact that those sand dunes are active, right? So probably at some point, Ingenuity will get buried. Now, whether that happens in 1,000 years or 1,000,000 years, that's not my area of expertise, but eventually it will get buried. I don't know if there'll be humans on Mars by that time. I think if there are, maybe they'll come and make like a little tourist trap.
Yeah,
tourist location.
A roadside tourist trap.
Come visit Ingenuity. I don't know, but so it's going to stay there for the most part, other than getting buried. And then we are going to do something with it. Our wings are clipped. We're not flying anymore.
Right.
We can still take solar data. We can take temperature data. We can still pull all this data down. We can take pictures and watch the sand move across. There's still stuff we can learn, even though we're sort of landed in the sand dunes. Eventually the rover will trundle its way out of telecom range, and then you'll be that'll be it. We are going to store the data, so we recently did a flight software update so that the data doesn't get wiped, and so we've got something like 20 years of storage space. So we'll just keep taking data every day for the next 20 years, and if the rover comes back, and we'll just pull all that data down. We'll have like 10 years of solar trending, depending on when the rover comes through.
Yeah.
Still living on. That's amazing, though. It's still alive.
Still doing science. Somebody just needs to come visit it so we can get the results.
Yeah.
That's right.
I've seen this coming through chat. I got to ask too, has anybody run a simulation like, all right, if we run the blades like this, we can actually sort of waddle across the surface in a useful manner. Has anybody run those numbers?
Love that.
Oh, man. I think you could wobble downhill.
Probably downhill, yeah.
I don't think you could wobble too much. I mean, no one's run those numbers.
Okay, you probably just dig yourself in, like.
Right, like even if you could somehow do it, the amount of time and that you would need to get anywhere useful would just be small. And like we were already kind of, like I said, at the end of what we could do
Yeah.
when we were flying. You know, now as a wobbly rover in a sand dune, I just can't imagine that anyone would give us money to work on that. You know, if you guys have been following NASA news, like money's pretty tight lately.
Yeah, yeah.
And so it's like even the rover is facing a tough time. So finding the time and the money to do some of these more creative things it's just not likely.
I would check that box on my taxes. If that box was on my taxes, I would check wobble the rover on Mars, wobble the helicopter on Mars, send some of my tax dollars to that, please. I'd be all about it. So
go tell your congressmen to get their act together. And
yeah. Oh, geez. Let me see if there's some more some questions here in chat. I know a ton of people have been asking questions. Somebody said, "Oh, it's a crashed RC helicopter, but it's on Mars." That's an important distinction that no other helicopters have.
Important modifier.
I think we could answer this. It's unlikely that the rover would try to drive to it because, like you talked about, rovers don't like sand dunes because the rover cannot really maybe get into the sand dune. It's more likely to dig itself in and get stuck, whereas y'all could take off and fly somewhere else, right?
It's both of the MER rovers eventually died from sand dunes. Perseverance has stayed clear. Curiosity has almost gotten stuck once. So it's not a terrain that rover drivers like to go anywhere near. In fact, even when we were going to rendezvous with the rover, they were like, "Can you guys come to the edge, a little bit past the edge, because we don't want to go over there. Like, we can meet you at the edge of the pool, you know?"
There was a question over here about the distance again. We had talked about like over a kilometer, and then there was a time when y'all went west and the rover went north. Let me see if I had that in the right. Where was that? There was a spot where you went west and the rover went north, and then you had to wait.
The 2 month dropout.
Is it this right here? It would help if I showed the map. On the western edge of Belva. This is flight 50. Is this the right spot you were talking about there?
Yeah. So flight 52 is that zigzag, right?
Yep. There's the zigzag.
Sorry. Flight 51.
51. Yeah.
Flight 51 is the zigzag, and flight 52 is that. Yeah. That
long range. Yeah. Okay.
Yeah. So that's the period where we're out of comms, but it wasn't distance. We were still only like 300-400 meters away from the rover.
Yeah, because the scale
down
problem
was that the rover was, this terrain doesn't look bad, but it's actually quite jaggy and rocky.
There's shadows.
The other side of a rock, so there's a big comms shadow. So it wasn't until I don't know when we got comms, but it was like maybe halfway. The rover was like halfway to us by the time we got in touch with it.
Were you waiting here before 52 or here at the end?
No, it's the end.
The end. Okay. So you went west over here like this, and the rover went north and did this sort of little thing where it got a sample. That's what that icon is. And then because of the terrain, like you can tell, like this is a satellite imaging thing. You look at these shadows and you can tell elevation changes because they cast a shadow. There's an entire thing about taking satellite photography at different times of the day because the shadows cast inform you about the terrain changes, right? But somewhere in there, it wasn't that far. You're well under a kilometer away, but just the terrain was just blocking the signal. A comm shadow, you said, right?
And it was a known issue, right? Like we have very good telecom predict maps. Like we can basically paint a color map of telecom strength from any 2 points on the surface. Like we knew we were going out of telecom. It was completely intentional because at the time, the rover traverse path was, for them to just book it due west. They were hot on our heels. They were going to be on top of us in like 2 days. And once they pass us, then we can't fly over them, right? Because of the keep out zone, right? So we have to stay ahead of the rover. So we're like, okay, it's a calculated risk. Let's go. And then, it's like a couple days later they saw something. They're like, let's just go north.
Yep.
Let's litter there for 2 months.
Like, we're just going to go this way.
Yeah.
Gotcha. Now since we've said we're asking questions, we've put our foot in the bear trap of now chat wants to ask 1,000 questions. I saw this one come through a lot, so let me hit this real quick. Dust in the motors and servos. Did y'all have to do anything different from off-the-shelf components to try and keep the Martian dust out of your components? Or was it basically just off-the-shelf stuff?
Yeah, that's an interesting question. So the rovers definitely do. Okay, so when Perseverance, they knew it was going to be a year-plus mission, right? So they have elaborate felt seals and labyrinth seals and Teflon lip seals and all sorts of seals, right? We don't have the mass for that, right? So, and also, again, we were a short duration mission. So no, we just ran them as is off the shelf and hope for the best. because there's only so much damage the dust can do in 30 days and 5 flights.
Right.
Right?
30 days and 5 flights.
And actually, if you go back and you look at the early engineering diagrams of Ingenuity, there were supposed to be dust trapping bellows. Can you pull up the swash plate picture
Yes,
again?
I can. Swash plate picture.
So like all through the CAD during the development phase, there were supposed to be bellows covering the swash plates. The swash plates actually move up and down on a carbon fiber shaft. So that there's a structural shaft that runs kind of from top to bottom, right down the middle of everything you're seeing here.
Yep.
Okay. And the swash plates, those aluminum pieces, they literally move. When you change the collective on the blades, the entire swash plate slides on that carbon fiber shaft.
Yeah, up and down
There's
like
no
that,
bearing
right?
or anything there, right? There's nothing that would make you think that that would be dust tolerant in any way. And so the intent was always to put like a little silicone bellows or something. And toward the end of the development phase, we just ran out of time and money. And we're like, look, guys, by the time we engineer this bellows, we will have introduced enough risk that it might not be worth it to put it on at all, not to mention we'll burn all the time and money. So let's just skip the bellows. And they didn't do it. And actually, it was one of the things we were really interested in. You know, we were going to try to get this post 3-year inspection, this close inspection from the rover using their kind of microscopic imagers. We wanted to see if there were like a lot of scratches or a lot of dust or anything else accumulating in there. It would have been really interesting. But
yeah,
all indications were she was running mechanically completely fine on the day of the crash. So yeah, I guess we kind of lucked out. Now, Ingenuity's a little weird because we're making our own weather, you know, in the downwash of the rotors. So that might be one of the reasons we were okay. But
you're not just sitting there letting dust affect you. You're affecting the dust, right?
Yeah. Actually, it's kind of interesting that there are a lot of dust settling models that tell you how quickly dust accumulates on Mars based on all of the experience we have on Mars.
Yeah.
All the missions and all the landers. And like Ralph Lauren's is a scientist. He's got a bunch of like, you know, dust models. Anyway, if you look at those dust models and you look at our solar array performance, we actually didn't accumulate dust as fast as we should have.
Okay.
You know, I know we showed that picture where it was just caked with dust, but in terms of array performance, we were something like 60%. And after that long of a mission, we should have been even worse than that.
Huh.
So it does seem like maybe the downwash that we were creating was doing something for us, but we'll never get to find out, really.
Yeah.
You know, we had some ideas on dust cleaning. Like I said, we gave up on most of them, but there were a few things I was going to try if we had more flight time.
I really wonder if something about the rotor spinning and the bearings that things are riding on, or the swash plate, or even just going through the atmosphere, it caused the helicopter to get a charge of some sort that helped it. It would either attract or push away the dust. Yeah.
That's totally a thing. You know, there's triple electric charging that occurs.
Nice.
There's like rocket plume charging that occurs. Like if you look at some of the Apollo missions, you get dust lofting, and everyone's like, how come the dust is floating in the air? Because it's space. There shouldn't be any air, right? But no, you get static electric charging when you get a lot of dust motion. And so, yeah, you absolutely can get that. In fact, it's something we looked at with Ingenuity. We were very concerned that we were going to create enough of a voltage by sitting here pushing dust through our rotor disc that we were going to like somehow fry the electronics or something like that.
Wow.
There's so much cool information on this. Like it's such a cool project. It's something that I think a lot of people have more experience. Like not a lot of us have a Mars rover, I guess, maybe an RC car that we've driven around, but it's so many robotic arms and stuff. But like a helicopter and the way that a quadcopter, or a little drone or something like that, those are so all over the place now. It's just an interesting thing to talk about. But all the different things that y'all came up with before you got there, and then the fact that it got there, and then you're supposed to fly, 30 days, 5 times. Yeah, okay, GPL, sure, 30 days, 5 times. And then the amazing success of the whole Ingenuity program. I can say that. I don't know if anybody else is going to say that, but I'm going to say that. Thank you so much for taking the time out of the weekend here to talk with us. Good grief.
Yeah, anytime. This has been a lot of fun.
No kidding.
Like get to walk through memory lane.
Yeah. Elysia, any end of show things here? Like we could sit here and probably talk for another hour, but we won't do that.
I mean, just again, thank you so much. This was so fascinating and really just really wonderful to recap everything, you know, just kind of say thank you again, you know, Ingenuity. You've taught us so much and are still going to teach us stuff if you're collecting all that information now even. if the rover ever comes back and you can grab it again, just learning about things on Mars in general without flying.
Yep.
But yeah, I can't wait to see, this was wildly successful. So I'm sure in the future, this is something that, JPL is going to be looking into doing maybe on a more sustainable, longer term thing for, scouting or for whatever.
We like to say that this is the Wright brothers flyer for Mars. It's like the first vehicle that enables flight.
And wasn't there a piece
once you show that it's possible, it's like everyone's imaginations start running wild. You can do all sorts of cool stuff.
Yep.
And wasn't there actually a piece of the Wright brothers flyer under the solar panel?
There was, yeah.
That's so cool. So cool. But yeah, no, thank you so much for doing this. We really wanted to kind of give it a send off. And I know it was obviously, in the news and everything. And everyone was wondering what happened with the crash. So this was really informative also in that regard.
Oh,
yeah. We're gonna try to do one final wave goodbye. We'll see if we can fit it in, but
nice.
We'll just do one final salute.
Like a helicopter blade salute. Nice.
Love
Folks, there's so many questions that have come through. There's so much fantastic comments. Folks are saying this was a super interesting show. Travis, you've been absolutely fantastic. Like the level of detail and just the openness to discuss things with us and answer all sorts of questions and stuff. It is absolutely fantastic that we were able to do this. But folks, I see all of your questions and all of your comments in chat. We can't answer all of them. They will be saved later. So maybe in a future show we can continue to talk about these sorts of cool projects. But thanks for everybody showing up today and taking part of the show. Also, all the donations for the Intrepid Museum to continue programming like this. I don't even have a list of what they all are. I see them scrolling by occasionally. I saw a lot of names that we say all the time supporting NSF and here supporting Intrepid Museum as well. So I apologize that I can't read them all back to you. But one of the best Astro Lives we've done for sure was the last comment that just came through chat.
Thanks,
Hope you can do this again. This is an incredible interview. One of the best for sure. Yeah. It's amazing to go through the mission. One of the best shows ever. I'm just literally just reading things.
Honestly, I felt like an emotional roller coaster. I feel like we landed, we did the journey, we lived the whole life of Ingenuity with you today.
Yeah.
I feel very emotionally fulfilled right now.
You have no idea how emotionally invested in these things you get, right? When you're waking up every day and you're like, okay, where are we going?
Where are we?
What happened? What's going on with us, right? Like it's like you're on the surface. It's
a robot, but it's real. It's your friend.
Yep. I was feeling it when you were saying like, oh, I wake up and I don't care what the weather's outside here. I need to know the weather on Mars. That's how I am with Starbase because we have solar powered installations and cameras and stuff. And I wake up and I'm like, oh, what's the weather at Starbase? And I'm in North Carolina. I don't even care what the weather here is. I need to know what it is somewhere else. So I was feeling you when you said that.
Yep.
All the different like you deal with the terrain, right? Where you're having to deal with the radio shadows and you land over a hill and so you don't have signal. We deal with the exact same things when we're bringing in remote video signals from Starbase. That's one of the big things that we do. And I can tell you places where if you walk over a sand dune and go down 1 meter, you will have zero signal on your cell phone at all. And if you walk 1 meter up the top of that sand dune, you have perfect signal and you get like 300 megabits down on 5G. Those sorts of things. I was even trying to work because I can bring up a map because we have all of our radios that talk around Starbase and we deal with the exact same things. And to hear that what we deal with is the same thing that y'all deal with, I guess, I don't know. I just think that it's really cool and it's really something that we can connect with. So
someday, hopefully we'll have a satellite, an upward-facing antenna, so we won't have to deal with it quite so much.
You don't have to deal with it quite so much. Something that can go over a dune or bounce off a satellite or something like that instead of being, I just walked over this dune and now I can't get anything. I don't. Anyways, all right.
Well, guys, thanks for having me. I guess I'm assuming you're wrapping up here, and
yeah, we are. We just don't want to wrap up, but I'm reading chat. Everybody's saying thank you. Let's go ahead and call that the end of the show.
As you can tell, I love talking about Ingenuity, so I'm always happy to answer questions. But yeah, it's been great. Thanks for having me, guys, and hopefully we'll see you again next time.
Yes,
all right.
Thank you so much, Travis.
Excellent.
I'm back on when we have Ingenuity version 2 on the surface.
Ingenuity 2.
We'll bring you back.
Ingenious Boogaloo or whatever you're going to call it. Folks, it's our guest today, Travis Brown, Ph.D., lead engineer for Ingenuity. Say that 10 times fast. Thank you. Or chief engineer. I said lead. Chief engineer for the Ingenuity program. Thank you so much for taking time out of your weekend to hang out here with us and chat and answering questions and stuff. You all know Elysia Segal as well. She's on all of our This Week in Space Flights. If you're trying to keep up with what's going on in spaceflight, we do a little thing every Friday to keep you up. We actually covered Ingenuity's progress in multiple This Week in Space Flights as little tidbits of news. So if you're looking for keeping up with cool missions like this Week in a Space Flight is a cool place to do it. And y'all know me. I'm Das. My mom calls me Das. That's not my real name. But that is going to be the end of the show today. So this is going to be the time where we all wave goodbye to you.
Wait.
Again. Oh, you have the thing. You do have the thing.
Things to plug.
Oh my gosh. She wants me to plug something. What do you want first?
I have a big announcement.
She has an announcement.
So the Intrepid Museum. This Tuesday, actually, we are going to be opening our largest ever temporary exhibition. It's called Apollo When We Went to the Moon. It is in our Space Shuttle Pavilion right underneath Space Shuttle Enterprise. So if you've never seen Enterprise, come to Intrepid and see the exhibit and Enterprise at the same time. But this exhibit is amazing. It is huge. It takes up the entire Space Shuttle Pavilion. It unpacks the history of the space race and the Apollo program, and it sets the stage for what NASA's doing now, going to the moon and Mars, obviously. And it uses interactive media. We've got a whole bunch of rarely seen artifacts from the U.S. Space and Rocket Center. There's a touchable slice of a lunar meteorite. Werner von Braun's drafting sets. There's Apollo and Soviet spacesuits, hand casts of the Apollo 11 astronauts. It's amazing. And this is the first time this exhibit is going to be on display in the Northeast. And best of all, it is all included with the cost of admission to the museum. And we have, if you see on screen, a very special discount code for you for general admission right now to celebrate. So if you use promo code Apollo Prague.
Who came up with that?
Apollo
Prague.
Purchasing your tickets, you can get $7 off. So be sure to use that. We would love to see you. It's going to be there all summer through September 2nd. And we also have a whole bunch of great programming planned in conjunction with it all summer long that are going to be, obviously more Astro Lives like this, but featuring, the moon and Artemis themed things. We've also got our free summer movie nights out on the flight deck every month where we're going to be showing moon themed movies, of course. We're going to have a full scale replica of an Artemis RS-25 engine out on our pier that you can come visit later in the summer. And our on-site astronomy nights featuring talks with engineers and astronauts, which you definitely won't want to miss later this summer. And then speaking of that, next month, April 26th, Das and I will be streaming live from the Intrepid Museum in New York City for a special Astro Live presented during our first on-site astronomy night of the year. Again, this is free. It's after hours at the museum from 5 to 9. Great stuff for the whole family. We've got educational workshops and demos. We've got stargazing out on the flight deck with the Amateur Astronomers Association. They're so great. And we'll also be doing a deep dive of the Orion capsule controls for the Artemis mission with an engineer. So it's going to be a lot of fun. Again, the whole family can come out, come visit New York City, come visit our amazing new exhibit, get your discount code, and say hi if you happen to see me or Das on site.
Nice. Elysia, I was looking at this image and I'm like, oh, there's dust and there's craters, and I wonder if a navigation could pick out the difference in the flat. And then I'm like, well, it's the moon. We're not flying any helicopters there.
Maybe they could, though. Maybe they might.
I would be very, very interested in how that would work.
I don't know how that would happen. Sure.
Travis, get to work. We want a moon helicopter now.
It's actually one of the things I'm working on right now is a rover, actually, a lunar rover.
No kidding.
Yeah, you look up, not down, when you navigate on the moon. You want to look at the sun and the stars.
At the sun and the stars.
Things are better than the surface.
It's true. Travis, your bio is very interesting. You are a jack of all trades with robotics.
Yeah.
You're working on a lot of projects. I feel like we could spend another 3 hours talking about all of your projects.
I've had like 20 jobs since I started at JP.
Nice. How about this, Travis? If you ever have something that you just want to talk about and PAO clears it, you know who to reach out to. Like,
okay.
we would love to talk about some of the other projects that are going on. So, y'all, that's going to be the end of the show. We've got all the plugs out of the way. Hey, New York Space Grant Consortium as well is how we make these things keep going, and y'all's generous support. That's why we're able to do this, but we really do have a lot of fun. Travis, I hope you had fun. Now will be the time at the end of the show where you all get to wave, and we say thank y'all so much for watching, and we will see you nerds later. I'm going to go ahead and roll the music, and then the show will be over. Thanks for watching, y'all.
And here we go.
chamber pressure looks good.
Doubling up. Roger, with planet.
Tango down to nominal.
Flight downside FD off. Say again, FD off. It's orange! 145! Oh my god! Oh my god! Decollage! Put that in the big bag, Segal.
343 unfolds to go.
Indeed. We rise together, back to the moon and beyond.
If the methane would be igniting in the flare, correct?
Yikes. You dead. We don't need any more of these.